with the current case rate, I would encourage you to wear one. I'll come back on once I've finished speaking. Welcome everyone to the fourth and final July lecture in physics for 2022. My name is Susie Shi. I'm the curator and host of tonight's event, and I'm also a senior lecturer in physics here at Roche, and I run a group in medical accelerated physics. So if you have any questions on that, feel free to ask me afterwards. Now, the theme of this year's series of lectures is all about quantum mechanics. So some of you, it will probably be your fourth lecture. I recognise many faces who've been coming every week. Thank you. And so far we've seen all about how quantum mechanics underpins the physics of our universe, fundamental particles, and cosmology. We've learned all about quantum computing, the potentially future of computing, and we've now all known how to program a quantum computer, which was really fun in the second week. And then last week we saw how to take quantum mechanics, which when we first learn it, we think, okay, it just applies to sort of a single particle or a couple of particles. And last week we saw how to bring all that together and scale it up to the scales of chemistry and materials and try and understand larger objects from a quantum mechanical perspective. Now this week, for our fourth and final one, it's another really important topic, which is the idea of thermonuclear fusion. And of course, because quantum mechanics underpins just about everything, quantum mechanics underpins this as well, and this is a topic that our lecturer tonight decided to address. So I'm not going to speak for much longer. The title of tonight's lecture is Thermonuclear Quantum Mechanics, the Elusive Promise of Fusion. It has been elusive for quite some time, as I'm sure David will tell us. And just to introduce our lecturer tonight is Professor David Jamieson. He's a professor in physics here in the School of Physics at the University of Melbourne, and the program manager for the Centre for Quantum Computation and Communication Technologies, if I've got that correct. He is also a very experienced public lecturer, so it's an absolute joy to have him speak for us tonight. So can you please put your hands together and give a big
Well, Susie, thank you very much. I appreciate that introduction. Does it feel like the molecules in this lecture theatre are moving really fast tonight? Yeah, it does. I'm feeling quite bombarded on all sides by high-speed molecules, so I'll take that off. It's too hot. Thermonuclear quantum mechanics, the elusive promise of fusion. I thought I'd take the opportunity in tonight's lecture to look at the link between quantum mechanics and fusion because I hadn't realised how intimately these two topics were linked until I had a chance to attend an after-dinner speech back in April at the Lawrence Berkeley lab, where we got an update on inertial confinement fusion. So I want to dedicate tonight's lecture to the memory of the late Professor Tony Klein, a man who was of immense influence over my career, indeed recruited me into my present role in the School of Physics way back in 1989. And here he is on his 80th birthday. We flew him down to Antarctica on the Qantas charter, and we had a whole bunch of students who were making measurements with flux gate magnetometers and dip circles and Geiger counters as we flew through the South Magnetic Pole on down to the Antarctic coastline, and then flew around and had the most spectacular views. And Tony was absolutely in his element. He was talking to everybody on the aeroplane. He grabbed the pilots and brought them down to show them the apparatus we were using, and he was just the ultimate physicist reaching out to the general public, and I miss him a great deal. And that is my son there, who came along as the chief photographer. But getting back to tonight's lecture, I'm very grateful to Susie, who, thanks to her contacts at the Royal Institution, organised for me to give a public lecture in London just a few weeks ago on the foundations of quantum mechanics in the fabulous ancient lecture theatre of the Royal Institution, where Thomas Young, in 220 years ago, demonstrated the Young's two-slit interference experiment, sometimes called the central mystery of quantum mechanics in that Young's two-slit interference experiment. So I thought it was a little bit cheeky that 220 years after Young demonstrated it in his own lecture theatre, I had an opportunity to demonstrate it again. And indeed, in this painting you see behind me at the entrance to the lecture theatre, there's a whole lot of bearded worthies, nothing wrong with that, using apparatus, some of which they got out of the museum and allowed me to use in my lecture. So Susie, I'm very grateful to you. Thank you very much for that. So while I'm thanking Susie, I should also mention that this tonight's lecture has an accompanying text which was written by our host, Susie, and let me recommend this to you because it's Susie's book, The Matter of Everything. It covers a lot of the physics that we'll be discussing in tonight's lecture. And Susie, could you autograph that for me afterwards? I'll just pop it over there. Thanks a lot. Great, much obliged. Right, so the context for tonight's lecture, being delivered tonight on the land of the Kulin Nation and the Wurundjeri people. And on the land of the Kulin Nation, there is now built the mighty city of Melbourne, a city of over 5 million people, and with an enormous thirst for power, not energy, power. Power is energy delivered at a prodigious rate. We need power to run our civilization, not energy, power. The energy has to be delivered at a prodigious rate, and that's power. And at the moment, this city draws its power largely from inadequate sources. I don't need to tell you about the headlines that have been in the newspapers over the last few weeks and months. We have a shortage of power. And indeed, fossil fuels cannot deliver the power adequately to run such a mighty city on the land of the Kulin. And so we urgently need to find alternative sources of power that are adequate for our needs first, and second of all, aren't going to take down the atmosphere and the biosphere. So we've got to stop emitting dangerous greenhouse gases. I don't need to tell this audience about that. So let me begin with some essential background physics to fusion power. I'll start in the beginning with the Big Bang. Don't worry, you'll be out of here before breakfast. In the Big Bang, there was an enormous burst of energy. Energy is mass by E equals mc squared that caused a relativistic change in the structure of space-time, where in the beginning there was only a space axis, and then as a result of what is almost certainly a quantum fluctuation at the heart of tonight's lecture, some of the space axis got converted into the time axis as is allowed under the rules of general relativity, and the universe then began to expand as a function of time. And in the beginning, the universe was purely radiation, but as it began to expand and cool, some of that radiation decayed into matter, antimatter-matter pairs. For reasons that humanity has not yet fully understood, the antimatter largely disappeared, and we were left with a universe made, as far as we can tell, almost exclusively of matter, ordinary matter. But if you do happen to meet an alien from outer space, don't shake their pseudopod or their hand, and just in case they're made of antimatter, just try and check it out first. But yeah, so now we've got protons and neutrons filling the first forms of matter, and electrons filling the universe. And then as a result of gravity and a result of non-uniformities, largely it seems driven by dark matter, that matter began to collapse under the pull of gravity and convert into, form the first stars. Steve, I just might take the lights down a touch. Yeah, so it sharpens up. Is that okay? Yeah, good, okay. So this is the sequence of events. There was the Big Bang, protons, neutrons, and some of those reacted to form the light elements in the periodic table, and then gravity clumped the rest into these long filaments, which collapsed under the pull of gravity, got very hot, and they ignited and became the first stars. Eventually they went supernova and seeded the universe with the the results from the nuclear reactions in those first stars, and then they eventually condense down via well understood processes to form the solar system that we inhabit today, with its load of radioactive elements that were created by the supernova events in the first stars, as well as the light elements that were created during the early stages of the Big Bang and the expansion of the universe. Now, all that stuff that was created during and after the Big Bang and by the first stars interacts with each other via one or more of the four forces of nature. As far as we know, these are the only ways stuff can interact with other stuff by exerting action at a distance. So the most familiar force of nature, of course, is gravity. Gravity holds us down on the surface of the Earth and also governs the orbit of the planets in the solar system, the orbit of the solar system around the centre of mass of our galaxy, and the interaction of the galaxies with each other in clusters, and generally the structure of the universe, because gravity is always attractive and has a very long range. The next familiar force is the electromagnetic force, which holds electrons in orbits around the nuclei in atoms and is responsible for the structure of the periodic table. This force can be attractive if the charges are opposite. Positive charges attract negative charges, or repulsive if the charges are the same. Then less familiar are the two nuclear forces. First of all, the strong nuclear force, and when I say strong, I mean strong. This is the attractive force between protons and neutrons, and between neutrons, that holds the nucleus together inside the atom. It's only a very short-range force, unlike gravity and the electromagnetic force, which are both very long-range. And then there's the somewhat mysterious weak nuclear force, the properties of which are still being understood in the particle accelerators and other experiments around the world today, which is responsible for particular types of radioactive decay. And these two forces are going to be the stars of tonight's show. Now, these forces have very different strengths. The strong nuclear force is the heavyweight in the 4. If I assign a number of 1,000,000 to the strength of the strong nuclear force that holds the nucleus together, then the electromagnetic force is 1,000 times weaker and has a strength of 1,000 on this scale. And then the weak force involved in radioactive decay has a strength of 10 to the minus 10. So it's 16 orders of magnitude weaker than the strong force. And finally, a distant runner-up is gravity, which is incredibly feeble. But of course, it's always attractive, so it's our most familiar force that governs all of us living at the bottom of a gravitational potential well that we call the Earth. So please keep that in mind. The strong force is really strong and way stronger than all the rest. Now, there are two types of nuclear power that are relevant to tonight's lecture. The first is fission power, where a uranium nucleus, typically uranium, but it can be other heavy elements, is bombarded with a slow neutron that causes the nucleus to split in half. Now, this uranium nucleus is held together by the strong force between the protons and the neutrons inside the nucleus. And when the neutron comes in, it causes it to oscillate violently until the left-hand side of the nucleus becomes out of range of the right-hand side of the nucleus, and then the electrostatic force kicks in and blows it apart into two fragments of roughly equal mass and a couple of leftover neutrons on average. And the nucleus of an atom was discovered for the first time by Ernest Rutherford way back in 1910, and it took humanity only about 35 years before Enrico Fermi built the first uranium pile and made a chain reaction so that this fission process just continued indefinitely, subject to control rods to absorb the neutrons to stop it getting out of control. So that's a remarkable progress in the understanding of the fundamentals of nuclear physics. Discover the nucleus, 35 years later, figure out how to split the nucleus apart and liberate energy. A nuclear reactor, in other words. And of course, this source of power is widely exploited around the world, particularly in France. Now, the other type of nuclear power comes from the opposite process. Rather than splitting a large nucleus into fragments, two lighter nuclei are joined together. These are two rather exotic nuclei. This is a deuterium nucleus, which is like hydrogen. It's got one proton and one neutron, and this is an even heavier version of hydrogen with one proton and two neutrons called tritium. And by forcing these together, they fuse and spit out the spare neutron and form a helium nucleus, and in doing so, liberate energy. Now, this is what is trying to be done artificially in the International Thermonuclear Experimental Reactor, more on which later. And so everywhere you see the word fusion, it should be glowing red hot, because that's going to be the topic of tonight's lecture, not fission. Get rid of that neutron. Okay. Now, the reason why energy is liberated from these two processes is because the mass of the fragments that happen after the reaction weigh less than the mass of the parent nucleus. So if you weigh a uranium nucleus and compare it to the mass of the two fragments into which it's been split as a result of the chain reaction in the nuclear reactor, you'll discover the two fragments weigh less than the original parent nucleus, even though it's the same number of protons and neutrons bound together with the strong force in each of the fragments. And this mass difference, which is, can be converted into energy, is converted into energy via E equals mc squared, or in this unfamiliar version, m equals E over c squared, arises from the binding energy that holds the big nucleus together. So there's less binding energy in these two fragments, and the missing energy appears as kinetic energy after the big nucleus splits in half. So the fission fragments weigh less than the original nucleus, and the excess mass is available as energy for technological applications. And the idea of generating energy with this process was perhaps first elucidated by Enrico Fermi himself, who later went on to build the first experimental reactor way back in 1923, where he discussed the possibility of using the nuclear binding energy to liberate the nuclear binding energy to make heat and hence electricity. Fusion, on the other hand, here we see what a reaction that occurs in the sun. Here are 4 protons, which weigh more than the helium nucleus, which they become after they fuse together, and there's a bit of nuclear rearranging going on. And measured per nucleon, or per proton and neutron, the amount of energy that is liberated with this process is enormous compared to the fission energy from the previous slide. So these two diagrams are not to scale. And surprisingly, around the same time Fermi was speculating about liberating energy from fission, Arthur Eddington in the UK thought that we could liberate energy by fusion, and indeed perhaps this reaction even powered the sun. A few details to be worked out in 1923, but again he discussed the possibility of using E equals mc squared in a fusion reaction to release the nuclear energy. So it's just taken a lot longer to the 35 years for fission for us to get the hang of fusion, and we still haven't got there yet. So this is now a diagram of all the elements you've probably ever heard of in the periodic table. On this graph, so we've got the light elements on the left, and then we go gradually through chlorine, iron, arsenic, dysprosium, hafnium, gold, bismuth, and finally uranium on the horizontal axis. And on the vertical axis is the amount of binding energy tied up in making the nucleus, divided by the number of nucleons in the nucleus. So we can see that heavy hydrogen, a proton and a neutron, is very tightly bound. So is a helium nucleus. Has a low binding energy, I beg your pardon, low binding energy down on the vertical axis here, and the binding energy gradually increases as you go up the periodic table until you get to the most tightly bound nucleus, which happens to be around iron 56. Ordinary old iron. Oh, no, that's aluminium, but you get the idea. It's the most tight configuration of protons and neutrons that exists in the periodic table. So you can see, therefore, by joining together these lightly bound light elements to make iron 56, you can release the binding energy from fusion. Or alternatively, by splitting apart the heavy atoms, the uranium, to make iron 56, you can liberate energy. And you can see on this diagram, the amount of energy you liberate by joining together light elements in fusion is way more than the energy you get from splitting apart the heavier elements in fission. So that's why fusion is such an attractive prospect for generating energy to power our civilization. There's lots of power available if we can only figure out how to do it in a technological context. Now, let me explain the mechanism of how fusion works. And to do this, we have to invoke the strong nuclear force. Now, I like to think of a neutron and a proton as an object that's got a hook sticking out. A very strong hook, but it's a very short hook. And this hook is a cartoon representing the strong nuclear force. So here's a neutron, and here's a proton, which approaches it. There's no force between the proton and the neutron because the neutron is uncharged, but the proton has a charge of +1. And when the proton gets close enough to the neutron, the strong nuclear force hook, which is only a very short one, engages, and we hear snick. You know, it's a cartoon, but you can imagine the two hooks going snick and hooking together very, very strongly once they get close enough. So that's a nuclear snick, very loud. But you can see here the strong nuclear force is very short range. And this is a diagram showing the force as a function of separation. Nothing much happens until they get very close, and then they bind together very strongly, representing the dip here. The force pulls them together very strongly, and because these are macroscopic lumps of matter, you can't superimpose the neutron on top of the proton. They can't occupy the same space at the same time, so it becomes repulsive at really short range to prevent them overlapping. And this also works for two neutrons interacting. But we have a problem when we try and make two protons interact. Steve, can I go to the pith balls, please? So what I've got in the first demo here is two model protons represented by two polystyrene spheres that have been sprayed with silver paint. And I've got Steve to connect them up to this old power supply that came out of a photocopying machine. Have we got them?
Yeah, we've got them. It's pretty... collection.
Can we see them? I don't think we can quite see them. Have we got a torch handy? We could just... Oh, there they are over there. All right, I think you can just about see them. Right, let me energise the power supply and we'll charge these both up positive. Whoa. Okay, notice they've repelled each other. They've pushed each other apart because they've both got a positive charge and they can't approach each other anymore. It's like there's an invisible spring consisting of the electric force between the two spheres. If you want to have a close-up look at this afterwards, you can come down and flick the switch on and off yourself and see the two balls push each other apart due to the electric force. So while we've got the camera, Steve, why don't we do this one? Another way of looking at this is to imagine that a charged particle is a large hill if we look at a gravitational analogy. And if I have another charged particle represented by this ball bearing, you have a repulsive force between the two particles. And you can also see that you can't get to the top of the hill with this apparatus because the hill is too high. So the repulsive force prevents my red proton engaging with my green proton. And if I don't hit it head on, we get a scattering event as the repulsive force pushes the proton away. So this is a gravitational analogy of the electric force. Now what I like to do is flip this upside down and turn it into an attractive force. And so now, proton-proton fusion. But that doesn't happen in nature because the protons repel each other. But this is the flip side, literally, showing an attractive force between the proton and the, a little bit of an orbit there, and the potential well. Okay, so that's what happens when we have equal charges interacting. They repel each other. So if we can go back to the presentation. Very nimble with the touch screen there. Terrific. Okay, so look what happens now when we have proton-proton interactions. First of all, there's the Coulomb spring, the repulsive force. Here's the proton, and it was travelling really fast. And it was travelling so fast it was able to compress the Coulomb, the electrostatic spring, until we had the snick when the strong nuclear force was able to come into play and engage, and the two protons are now bound together. But tightly coiled up between the two protons is the electric force that's pushing them apart. And remember, the strong nuclear force is 1,000 times stronger than the electric force, and so this can be a stable configuration, providing you can get the protons close enough so that they stick via the strong nuclear force. And so the force field between two protons looks a little bit different to the green one between a proton and a neutron, or between two neutrons, because now we have this potential barrier that has to be overcome before the two protons can link together and fall down here and become stable with that tightly coiled spring in between. Now, I said that the strong nuclear force had a short range. In fact, the length of this hook is only about 10 to the minus 15 of a metre. That's pretty small. And for convenience, we call that 1 Fermi, named after Enrico Fermi. So that's a metric unit you probably haven't heard of, but I hope you can use it in your conversation in the next week or so. Oh, that's a few Fermis, that distance, meaning it's really close. Okay, great. Now, here's the problem for fusion. So here are two protons. I haven't bothered including any neutrons for simplicity. As I mentioned, there's this very strong Coulomb repulsive force because the two protons have the same charge. And this is the electric force with a strength of 1,000 repelling them. And here is now an agent and another agent pushing the protons together. And there is the Coulomb force holding them apart. Now, if the agent is not strong enough, it won't be able to, the agents aren't strong enough, they won't be able to push the protons hard enough until the hooks engage and we have fusion and the power is released from the binding energy. So the trick for making a successful fusion power station is to figure out a way of pushing the light elements together to overcome the Coulomb spring, the electric spring, until the nuclear force is close enough to engage and bind the protons together and make new elements and release the strong nuclear force binding energy. So another way of drawing this diagram, which is perhaps easier to see what's going on, is to consider the electric force sets up a barrier to fusion. And I kept calling it the Coulomb barrier after Charles Coulomb, who first understood the nature of the electric forces between charged particles and worked out that the force between two charged particles is given by a constant times the product of the magnitudes of the two charges divided by the square of the distance they are apart, a formula very reminiscent of the one that applies to gravity. So here is a proton approaching another proton, and there is the Coulomb barrier, or the created by the electric force that prevents them from engaging. Now what we'd like to do is overcome that electric force, the Coulomb barrier, but it's like climbing a mountain. So here's the proton coming in from one direction, here it's coming from another direction, and it's very much like this Hot Wheels demonstration, which is just ideal for demonstrating thermonuclear fusion. So what I've got here is a very sophisticated bit of kit, Hot Wheels outfit. And I've got two cars starting from each end of this outfit, and this hump in the middle represents the mountain, the Coulomb barrier between them. Oh, all right. So now I need an assistant to launch the other car. Steve, can you do the honours? Okay, so on the count of three... Oh, yep, great. On the count of three, we're going to attempt to fuse these two cars together. 1, 2, fusion! Ah, hopeless. No way, they can't get over the Coulomb barrier. Let's try that again. 1, 2, fusion! Ah, pathetic. So in other words, these cars are simply not going fast enough to get over the Coulomb barrier and have the happy event where a fusion event occurs when they collide at the top of the hill. Thank you, Steve. We'll leave that to the end of the theatre, end of the lecture. So the problem of fusion basically involves solving the problem of how to overcome the Coulomb barrier. Great. So can you hit the AV option? That's great. Thanks, Susie. And get over this mountain created by the repulsion of the Coulomb force, the electric force. So this brings me now to part 2, the power from the sun, because obviously the sun works and has figured out a way to do this, metaphorically speaking. So the sun has always been a bit of a mystery up until just the last century to understand how the sun actually worked. I mean, the sun is such a fundamental part of our lives. It rises every morning, it sets every night, it's nice and warm, not in Melbourne, although it wasn't too bad today. Where does it get its power from? And once radioactive elements were discovered, it was realised the Earth was really, really old. So the sun has been cooking for billions of years. Where the hell does it get its energy from? So way back in 1863, people did the calculations and realised it probably wasn't burning coal. Sorry, coalition. Oh, no, sorry, there's no politics in tonight's lecture. Yeah, no politics, no politics. It's not coal. Coal, it would all burn up in just a few million years, and it's clear that the sun has been burning for much longer than that. So this article in Scientific American, I love it. Experts doubt the sun is actually burning coal. I love that article. Someone had to say it. So, all right, we've crossed coal off the list. What else is there? Well, surprisingly, the sun is very big and stuff keeps falling into it because the gravity is very strong. And so maybe it's just stuff falling into the sun and blowing up and causing the sun to be hot and stay hot for a very long time. So a couple of famous physicists, Helmholtz and Kelvin, back in the middle of the 19th century, did some calculations. What if stuff was falling into the sun, making it hot? And they calculated that given the gravitational field of the sun and the amount of likely stuff, it would only stay hot for about 20 million years, which was well known to be way too short a period of time. So that was crossed off as well. So it had to be something else. And it's amazing to me to think that my grandfather, who was born at the beginning of the last century, would not have been able to explain to you how the sun got its power from. It's such a fundamental thing in our lives, and yet the source of its power remained mysterious until the 1930s. And so finally, gradually, humanity got its head around where the sun got its power from. And this is an article from the International Thermonuclear Experimental Reactor website explaining the invention of thermonuclear fusion, which is where the sun gets its power from. So first of all, Ernest Rutherford at the University of Manchester in the 1910s up to the 1930s realised that tremendous forces were tied up inside the nucleus, those tightly coiled electrostatic springs, and that energy could be liberated. And then Arthur Eddington, a very creative guy, a very original thinker, said, well, maybe the proton-proton reaction is the basic principle whereby the sun gets its energy from, and not just the sun, but other stars as well. But his theory wasn't complete in a way that I'll explain in a moment. So it wasn't 100% successful, but he was clearly heading in the right direction. And then this Australian guy, Marcus Oliphant, who later went on to become the Premier of South Australia and the head of physics at the Australian National University, did experiments involving accelerating light elements like tritium and deuterium, colliding them together in an accelerator. So they were going fast enough, not like in our Hot Wheels demonstration, to overcome the mountain in between and fuse together. And he discovered that these reactions from artificially accelerated light elements liberated an enormous amount of energy, and this paved now the path to understanding the way the sun worked. And it was finally Hans Bethe, a terrific guy. I once had an opportunity to go to a colloquium given by Hans Bethe when I was a postdoc at Caltech. Unfortunately, I arrived 10 minutes before the lecture was due to start, and I had to stand out in the corridor and just listen to what the great man had to say. I couldn't get in the lecture theatre, it was so crowded. But in 1938, he cracked the code. He realised that it wasn't sufficient for the sun to be hot to trigger the nuclear reactions that power it. There had to be a role for quantum mechanics, which of course is the topic of tonight's lecture, as I'll explain shortly, and he finally worked out where the sun got its power from, building on the work that had gone before. But my desire is to see a technological application of fusion. The sun is all very well, but it's a bit inconvenient. Lyman Spitzer in 1958 said that we might be able to create a fusion plasma in a machine on Earth that causes light elements to fuse together, liberate energy, and we could use that energy to make electricity to drive our civilization. And so, of course, the machine was called a stellarator, a sun machine, but as we'll see, the machine does not use the nuclear reactions in the sun because they're too feeble, and I'll explain why in a minute. So what Eddington thought was that when things get very hot, when a gas gets very hot, the gas atoms go very fast. Let me see if I can bring up this demonstration for you. Yep. Yep. Ooh, yep. Okay. And we're going to turn everything on. Okay. Now, this is a cartoon, but it's a very fancy cartoon. I've got a container to put gas in here, and this is using only classical physics, no quantum mechanics here. And I'm going to cause a whole lot of gas atoms to move into this container. And over here, two histograms are going to appear of the speed of the atoms and the kinetic energy of the atoms. Okay, so here we go. Let's pump some gas atoms in. All right, now they're all going at the same speed, but as they begin to hit the walls and interact with each other, I might have put a few too many atoms. No, that's good, that's good. They begin to exchange their original energy with each other, and pretty soon they're moving at different speeds as the speeds more or less randomise as a result of the myriads of collisions. But you can see over here in this histogram, the atoms are now sharing the energy. So most of them have only a little bit of kinetic energy down here on the left. But there is a long tail in the distribution, and some, by just random collisions, have acquired a lot of energy and are moving very fast. And you can see in the speed distribution there's a high energy tail where a handful of atoms are going very fast, even though the temperature of this sample of gas is only 300 Kelvin or 27 Celsius. There is a small number of atoms that have shared the energy in such a way that they're now going really, really fast. Now that's good. That's what we want for a thermonuclear reaction. Our matchbox cars on the Hot Wheels track were going too slowly to get over the potential barrier. But maybe in a sample of very hot gas, there'll be a few atoms at the high energy end of the speed distribution who have just picked up their high speeds as a result of all these random collisions, which could instigate fusion. All right, so that's the basic idea, taking a lesson from just ordinary classical thermodynamics. And that those particular distributions that you saw in that simulation are called the Maxwell-Boltzmann distribution after James Clerk Maxwell and Ludwig van Boltzmann, who discovered it. So let's go back to the sun now, equipped with this new result about gas atoms, some of which go very fast. So Eddington said, maybe the atoms at the high energy end of the Maxwell-Boltzmann distribution could be going fast enough to surmount the Coulomb barrier, to climb the mountain until the two strong nuclear hooks were able to overlap against the Coulomb repulsion and fusion would occur inside the sun, which was known to be a very hot object. So it should have lots of gas atoms that are going really fast. And so people did the calculations and calculated the probability of finding a really fast gas atom, a hydrogen atom, a proton, which would collide with another proton and fuse together. Unfortunately, the sun was found to be not nearly hot enough for the nuclear forces to overlap. And so Eddington's idea languished because he hadn't applied quantum mechanics to the problem. So this is what he hoped, that we've got this barrier, and he hoped that the classical trajectories of the atoms in the gas would be enough to go over the top, but it turned out there wasn't enough gas atoms going fast enough to go over the top so that fusion could occur. The energies were just too low, and so the classical trajectories were forbidden. They couldn't get over the top, and fusion did not occur. And it wasn't until Hans Bethe realised that there was a quantum mechanical solution to this problem. Because you have to remember, a proton is a quantum mechanical particle. So when it approaches a barrier like this, it turns into a wave. That's what I was demonstrating in Young's lecture theatre in the Royal Institution in London just a couple of weeks ago. So let us turn that proton into a wave. It hits the barrier and reflects off it, just like waves do. But a quantum mechanical wave has an extra attribute. It can penetrate into the classically forbidden barrier and pass through it, somewhat attenuated, and come out the other side, bypassing the peak. And when you apply quantum mechanics to the thermonuclear processes in the sun, or when Hans Bethe applied quantum mechanics, the tunnelling process that allowed the barrier to be penetrated, he cracked the code and finally figured out where the sun gets its energy from, and of course he got the Nobel Prize. And indeed, since then, the applications of quantum tunnelling through classically forbidden barriers has led to 5 Nobel Prizes so far. Now, I can demonstrate this to you in the lecture theatre with a somewhat electromagnetic analogy. What I've got over, I'll have to do it around here. What I've got over here, we don't need to change the video for this one. What I've got here is a microwave transmitter. Okay, it's not emitting classical particles like protons, it's emitting photons, but the physics is the same. So photons instead of protons. And over here I've got a microwave detector, which I'll set on 2, right? Yeah. And so if I take the transmitter and put it in front of the detector, I can detect the microwaves. Now, when I send the microwaves into this block of paraffin, they scatter, and in fact they reflect off when they come through from the inside this surface and bounce out. So if I put my detector here in a straight line with the transmitter, can't hear anything. So the microwaves are not passing through this block of paraffin because they're totally internally reflected off the inside of this interface. But if I swing the detector around here, I can pick up the microwaves because they've bounced off this surface and they've come out, and they've come out at an angle of 90 degrees. So nothing over here, they've all come out over here. But here I have a second block of paraffin. Couldn't we have polystyrene next year, Steve, please? And I'll slide that into the gap here. And now I can hear a signal. So in other words, the microwaves are tunnelling through this classically forbidden gap, passing through the block of paraffin into the detector. Quantum mechanical tunnelling with a photon right here in the lecture theatre. And look, there's the gap. And if I close the gap up and reposition this, the tunnelling gets even better because the gap gets smaller, and so the quantum tunnelling becomes more effective. So that is what was missing from Eddington's ideas that Hans Bethe put in and figured out the thermonuclear fusion solution of where the sun gets its energy from. So this is sort of a summary of the results so far. This is the Maxwell-Boltzmann distribution as a function of energy. This is the quantum tunnelling probability between 2 protons to fuse, and the product of those two gives what's called the Gamow peak, which shows where fusion is possible in a hot object, and hence the name thermonuclear fusion. Now, the most abundant element in the universe is hydrogen in the form of protons with an electron orbiting, and so in the sun, protons ionised because the sun is very hot and the electron is ripped off, so it's not hydrogen gas anymore, it's just a plasma of protons and electrons. Occasionally, our 2 protons will fuse together and turn into the heavy isotope of hydrogen called deuterium, and then another proton will collide with the deuterium to create helium-3, and then another chain produces another helium-3, and then those 2 helium-3s can fuse together, liberate an excess proton or 2, and create the stable isotope of helium, ordinary helium-4. And in each place where there's a yellow star here, energy is released that eventually converts to heat. So, terrific. Proton-proton fusion. Let's do it on Earth. No. You may not, for the following reason. You'll notice the first step in the proton-proton fusion chain that converts 4 protons eventually into one helium, involves the liberation of an electron and a neutrino. That's that mu symbol. Now, a neutrino interacts with matter via the weak interaction. And so therefore, this first step involves not the strong nuclear force, it involves the weak nuclear force. And so this reaction happens incredibly rarely. The only way you can make use of this reaction to generate energy is in a huge reactor, so that this very improbable reaction occurs frequently because the reactor is large, as big as a star. The rest is okay because it involves the strong nuclear force, and that's all right. You can do that on Earth, but you can't do the first step. It's too weak. So the PP cycle in the sun, the proton-proton cycle, works just fine at the temperature of the sun, about 10 million degrees, overcoming the Coulomb barrier, and very occasionally the weak interaction allows the conversion of two protons into the next step in the chain. So if it wasn't, and this temperature, by the way, is 1,000 times too cold to allow that to happen just by the Boltzmann distribution, but the quantum mechanics steps in and bridges the gap and allows the shortcut to the quantum shortcut to tunnel through. Now, this is why this reaction is not suitable for technology, and I've used this fancy font to show, this is talking about the future. Here is the weak interaction. Imagine you had a current of protons instead of a current of electrons like you normally have in a wire, and you had an ampere of protons flowing through space, colliding with a block of solid frozen hydrogen. So there's lots of protons available. And you ran that beam of 1 ampere of protons, that's quite a lot of current, down onto this block of solid hydrogen for 10 years. You would get one proton-proton fusion reaction because of the extreme feebleness of the weak nuclear force. And so we're impatient to get our power. This is not rapid enough to be useful to charge my phone, or to run my Tesla, if I had one, I don't, or to run my university with its 50,000 students, or to run the city of Melbourne on the land of the Coolin with its 5 million people, all surfing the internet, driving cars, taking trains, flying all over the place, and generally having a terrific time. So, sadly, what happens in the sun is not suitable for technology. So this now brings me to the third and final part of my talk, artificial fusion. How do we crash our particles together hard enough and frequently enough so instead of using the weak nuclear force, we can use the strong nuclear force and build a reactor small enough to put in a city or somewhere nearby, not something as big as a star. So alternatives to proton-proton fusion involve the other light elements, the light isotopes of hydrogen. This is ordinary hydrogen, a proton with an electron in orbit. This is deuterium, sometimes called heavy hydrogen, with a proton and a neutron and an electron. Or there's a radioactive version of hydrogen, which is a proton with 2 neutrons and an electron called tritium, with a half-life of about 12 years. And in the old days, all the emergency exit signs that you see around the place had tritium in there to keep them illuminated, and you had to replace them every 12 years as they gradually faded away. But I don't think we're allowed to use tritium emergency exit signs anymore. Right. So we need a fusion reaction that's governed by the strong interaction. I looked it up on Amazon. They offered this, but that's not what you want. That's from a Hollywood movie. So deuterium-tritium fusion is a possibility. That's governed by the strong interaction, and that's what the International Thermonuclear Experimental Reactor uses in this plasma confined by very strong magnetic fields. One further demonstration, Steve. Again, I don't need the... oh yeah, okay, it's for the people watching at home. So the basic idea here is to take charged particles, the protons and the tritium and the deuterium, put them in a very strong magnetic field. And unfortunately, the apparatus I need to use to demonstrate the magnetic bottle hasn't reached here yet because of the pandemic. But you can see if you've got a strong magnetic field, this is a beam of electrons instead of protons, but the principles are the same. You can bend them. And if my magnet was stronger, I could bend them back on themselves and have them orbit backwards and forwards in just a magnetic field. And so I've confined the charged particles in the form of the plasma in a way that their fusion can take place at very high temperatures with all these very fast charged particles. So magnetic confinement is the way ITER is exploring fusion. Susie, do you have a camera handy? Yeah, so before ITER there was JET, the Joint European Torus, and I happened to visit this facility way back in 1989 when it was fully operational, and they were very close to achieving thermonuclear fusion in 1989. And when I looked at the JET website for an update in 2022, it said, we're very close to achieving thermonuclear fusion in our tokamak. Now, in 1989, we didn't take selfies, so I don't have a picture of me visiting this. So I've just enlarged it, and could you take a selfie of me with...
Yeah, 1 second.
No, don't worry, it's all right. We can do it afterwards, but...
Just need some light on.
Okay, yeah, here we go, a selfie. No, you have to stand over there.
If it's a selfie, I've got to be in it.
Oh, you've got to be in it as well, but we have to have that in the background. Yeah, there, I just enlarged it, so it's to scale. Yeah, JET in the back. Yeah, look, we're really there in 1989. Oh, fantastic. You weren't there in 1989.
I was a bit smaller.
Yeah, a bit smaller. All right, but you get the idea. All right, so I can put that on my Facebook page, so I was there. All right, so it's huge. It's a big machine, and it still doesn't work. But today, there are new ideas for compact versions of JET with superconducting magnets, and these things are under construction today. There's been a resurgence of interest, and there are these really weird-looking machines to keep the plasma confined and interacting. This is called a stellarator, like Spitzer's original idea, being built in Germany, again using new technology to hold that plasma together and make it hot enough, long enough for fusion reactions to occur. And these guys are using compression of the plasma with a liquid metal and all these pistons to try and force the deuterium and the tritium nuclei together so that they fuse. And this is the artist's impression of the power station. It looks so nice, it has to work. Okay, and this is ITER. You can see the facility being built. It's a multi-billion-dollar, $10 billion enterprise, but it may not be ready for 20 or 30 years. Over in Berkeley, they have gigantic lasers where they blast a little sample of tritium and deuterium with these lasers, causing it to implode, and they do indeed see fusion reactions, but at the moment the amount of energy they get out is small compared to the power they put in from all the lasers. This is called inertial confinement, but it's looking promising, but there's still maybe decades to go. There are other fusion reactions, deuterium-deuterium fusion or deuterium-helium-3 fusion, but these are unfavourable because they need even higher temperatures than deuterium-tritium, and it's problematic to make the plasma. And of course, this science fiction movie, I don't have any real experiment to show you, suggests that one day humanity will mine helium-3 from the lunar regolith and build fusion reactors using this technology. And just lately there's been this new idea of boron, ordinary boron-11 fusing with a proton to create 3 alphas, no dangerous neutrons, but this needs extremely high temperatures for this to work, and so I think this is a long-term prospect. But the design for the reactors have been published and they're under construction. Have I got just 30 seconds to show this video? Okay. So this is a video released by a company called First Light Fusion, a new approach to fusion that involves a combination of mechanical and electrostatic forces to create a fusion reaction. So there's this little cube dropped down into the middle of this reactor along with a pellet of fuel, and the two things collide at enormous velocities, and as a result of the shock wave that passes through the little cube during the collision, the fuel is enormously compressed, bang, fusion. The energy is dumped into the walls of the container, which has got lithium, liquid lithium going down, and that goes to heat. Now you might say, well, boy, all of that stuff looks very high tech and is going to be very expensive. Correct. But is it expensive compared to what we do now with fossil fuels? So I don't think people realise this, but the Gorgon gas project in Western Australia cost $53 billion, generates an electric power equivalent of only 1.5 gigawatts, Melbourne needs 10, and emits enormous amounts of CO2. Likewise, the Hinkley Point C nuclear reactor in the UK, $36 billion and counting, but an enormous amount of power, no CO2. And the Adani mine, $22 billion in the first phase, 9 gigawatts of power from burning the coal, 130 megatons per year of carbon dioxide. So a fusion reactor on this scale actually seems rather modest, should we figure out how to get it to work. So let me conclude. My colleague at the Lawrence Berkeley lab, Thomas Schenkel, like me, is very interested in new forms of computation involving quantum mechanics, and you saw the lecture from Lloyd, those of you who came to one of the earlier July lectures this year. Thomas says, okay, fusion is essentially a quantum mechanical process. We've been modelling this quantum mechanical process using classical computers. It's very hard to use a classical computer to model a quantum mechanical process because the quantum mechanics is much more subtle, deeper and more complex than any classical process. So he convened a workshop a few years ago on using quantum computers to model fusion and try and find a bypass around the classical barriers that are in the way from harnessing light element fusion. And ladies and gentlemen, I can tell you the news is good, but not ready for publication yet. So I'm looking forward to a quantum mechanical simulation of a new type of thermonuclear reaction that can be built into a human scale power station that will eventually provide the clean power we need to run our civilization without destroying our biosphere. Thank you very much for your attention.
Thank you, Dave, for another wonderful July lecture. I am aware that we're a couple of minutes over the scheduled time, so if anybody does need to sneak out, you're welcome to. We won't catch you on camera. But I'm also sure that many people probably have lots of questions. I'm going to kick off with one while you think of it, and pop your hand up when I come back to you. Dave, fascinating lecture. All the fundamentals based on quantum mechanics seem to be really clear. The promise seems to be clear, and we're making progress, albeit slowly. What do you think are the biggest challenges in some of those reactor systems? For example, the one I think that we've been looking at the longest is sort of the stellarator or the tokamak concept.
70 years.
What physics is getting in our way? Or engineering?
Well, the simple answer, because I know people have to go and have breakfast eventually today, is that we're using the Maxwell-Boltzmann distribution to create the high-speed ions in the plasma that we hope will fuse together. And we already learned our lesson when Eddington proposed that back in the 20s and realised it wasn't going to work, and yet clearly it does in the sun. It should be too cold for that to work because he didn't know there was a quantum mechanical aspect to the reaction. Now, I wouldn't be surprised once we look in detail at the spin, at the baryons, at the leptons, at the standard model, which is governing the way those ions interact, and use the quantum mechanical models that can handle the vast parameter space, we will find a way through. In the same way that Bethe found a quantum mechanical way through to show what Arthur Eddington had missed 20 years earlier. That's my hope.
You just laid down a challenge for our department to work together on that.
Go for it.
Right, questions from the audience. If you have a question, pop your hand up, and either I or Matt will bring a microphone to you. Right at the top there, Matt, could you bring a microphone at the top? Yeah, thanks.
I'd like to know what the difference between the strong nuclear force and the weak nuclear force. And to me, they just sound like totally unexplained entities, or whatever you want to call them.
So,
By describing something we don't really know much about, it seems.
okay, I hope I didn't give the impression we don't know much about them, because actually we do know an awful lot about the strong nuclear force and the weak nuclear force, and they are modelled by what we call the standard model for particle physics. See the text, the assigned text for the course, which will explain more about it. So we understand the quantum mechanics of the weak nuclear force that governs radioactive beta decay and other forms of interaction through the exchange of W and Z particles. That's the quantum mechanical model, and we can do calculations in great detail using what we understand, and we test them at CERN and the other particle accelerators, and our understanding is near complete of the weak nuclear force, and the same with the strong nuclear force. I called it the strong nuclear force in this lecture, but you may have noticed on the slide I actually said colour force, in brackets strong. The strong nuclear force arises from the gluons that hold the quarks together inside protons and neutrons. When they get close enough together, these gluons form those hooks that you saw sticking out and link up with an adjacent set of quarks and gluons in the centre of the next particle. And again, we know from the standard model for particle physics exactly how that process works, and we can do calculations to extremely high precision. So yes, I hope I didn't give the impression that we didn't understand either the strong or the nuclear force. In some ways, we understand them better than we understand gravity.
I'd agree with that, yeah. Some of the best, most precise calculations that would be all. Right, next question. If you can come down, is someone in this specific... No, the hand's gone down? Oh, here we go. Yep. Thanks.
Thank you. I used to lecture thermodynamics at RMIT in chemistry, which is to do with energy and mass and heat and work and things like that at the macro level. My question is there a current thermodynamic, are there current thermodynamic laws like there are in standard thermodynamics at this lower level that you're talking about of the standard model? Is there a thermodynamics of the standard model to deal with heat and energy in the way in which we've actually used the steam engine to bring it down to the layman's level? How we use the steam engine and other sorts of levels to produce work in our motor cars, etc., etc.
Yeah, that's an excellent question, and the short answer is yes, there is. When Josiah Willard Gibbs laid down the full majesty of thermal physics, which we now call statistical physics, which I happen to be teaching right now and just came from a lecture before I came here, he introduced the concept of the chemical potential. And as a physicist, I always feel uncomfortable introducing something with the word chemical in it in my physics lectures, because we do physics here, not chemistry. However, you can write down a chemical potential for all of the forces in the standard model and use the same thermodynamic parameters or the same thermodynamic principles to calculate nuclear and subnuclear reactions by generalising Gibbs's chemical potential, introduced more than 100 years ago into the new sorts of potentials that Gibbs would never have known about. So the short answer is yes. The longer answer is it's complicated.
I might go to another question if that's right. One last question before we close out for the evening. The person in the blue jacket in the middle here has had their hand up for a while. Matt, have you got the... Thanks. Sorry, up here in the blue cover, yeah.
Oh, hi, thanks for a great lecture. Just talking about fusion or fission, when you start off with protons and neutrons of a certain mass, and afterwards you've still got the same number of protons and neutrons, but collectively there's less mass. So does that mean each proton and neutron has a little bit of mass whittled away, or is it the proton that is of less mass, or the neutron, or how does that work?
No. No, all the gluons and quarks are still there. It's just the way they're bound together changes. In the same way, if you took a mole of oxygen and 2 moles of hydrogen and you burned them together, you get a mole of water. And a lot of heat comes out, right? Hydrogen burns fiercely in oxygen. Now, in chemistry, they tell you mass is conserved. Sorry. That heat comes from the difference in mass between the 2 moles of hydrogen, 1 mole of oxygen, and the 1 mole of H2O, because of the chemical bonds rearranging themselves into a lower energy configuration, and liberates the excess mass in the form of heat and light and other energy. So this is routine. Chemical reactions involve changes of mass, but the changes of mass are so tiny that the chemists multiply it by c squared, the speed of light squared, which is an enormous number, and use joules instead, the unit of energy. So I said this at a lecture, by the way, 20 years ago, and the ABC science show, Bernie Hobbs was the journalist, used it in one of her snippets on Catalyst or whatever it was in those days. And that comment that chemical reactions involve the change of mass converted to energy and heat and light and so forth triggered thousands of complaints from the general audience. And so the ABC lawyers came to interview me and said, why are you putting stories out that chemistry doesn't conserve mass when everybody knows it does? I said, sorry, you can't take me to court for explaining the laws of physics. I'm sorry, you can't. I answer to a higher court. Well, the laws of physics, I mean, you know. And so I had to have a dialogue with the most obstinate complainer who had taught chemistry for 30 years. And finally, at the very end, he said, all right, okay, even if you're right, the change of mass is so tiny, it's completely negligible. And I said, my learned correspondent is correct. The change of mass is almost negligible, and he's been multiplying it by c squared, E equals mc squared, and using E instead for all his career, and eventually he said, oh yeah, that's right. And he rolled over and the lawyers went away and left me alone. Yes! Thank you.
On that note,
yes.
I think another massive round of applause. Thank you so much for another wonderful lecture.
Thank you. Thank you.
And thank you all for coming out again on a Friday night. It's wonderful to see you. Of course, next year we'll be running the July lectures again, so have a look out for that on the email list. And if you're interested in seeing more public lectures as part of at the University of Melbourne on science topics, there is a science festival as part of Science Week coming up in August as well, so keep an eye out for that.
And Susie, would you be giving a lecture in Science Week yourself?
I am actually, 18th of August at Science Gallery, just outside university.
Excellent.
I'll be giving a lecture about the contents of my book, which is why I'm not speaking in this year's lecture series. So
okay, great.
thank you
Looking forward to it.
my lecture. And your book is now signed.
Thank you very much.
Thank you all.